and the next important and basic chapter is a mathematical representation of robotics. Okay, what is the meaning of this? So here, for example, if you take any simple robot, okay, so in this simple robot, this you see here, this is the fixed one, this is the fixed link, and this is another link, okay, and this is the one more link, and this is the end effector. So end effector, either it can be directly fixed to this, or it can rotate based on our requirement here. So why it is called as the end effector? Since it is at the end of the link, and this is the one which is used to perform our operation. For example, if you look at any industrial robot, if you otherwise you go to the YouTube and you type like a Tesla robot. So here what is happening? The end effector means the end link of the robot will grab the part, and then it will take you to the some other position, and then it will perform the different operation whichever we need it to do. So that is why it is called as the end effector, or sometimes it is also called as the tool. Okay, don't get confused. Tool is nothing but the end effector here. So these are the links. Different links are there, and how one link is connected to the another link? By using the link joints. So these are the joints here. So here in this case, for example, if this is a planar robot, if you consider this as a planar, then this in this particular case the joint is a revolute here. Okay, the joint is revolute here, and here also revolute. So sometimes you can use the slider joint also between these two, or sometimes you can use the spherical joint, or you can use the cylindrical, or you can use the universal joint or hooks joint. Okay, that we will see different types of joints. So here what is the basic thing we need to understand? The robot here is not a simple one body. A robot is nothing but our human body. So here in our human body also we have from here to here one link. In the hand, from here to here one link, and this portion is another link. So how these two are connected? See, it can rotate like this. So that means here these two are connected with a rotary joint, and this is from here to here, this is one link, and from here to here one link. How these two are connected? By using the one more revolute joint here. Okay, and here how this portion shoulder joint is connected? This is with a spherical joint. Why spherical joint? For example, this is going like this, one revolution, and this can go like this, another revolution, and it can go like this also, 3 revolutions. That means it is rotating about the 3 coordinate axis. Okay, so in the same way robot also constructed like that, and we have a links. Whenever I say links, you assume that unless otherwise stated, you assume that these are the rigid links. Okay, we have a flexible robots also. We have flexible robots also, and active research is going on that. But at a UPSC level, engineering services, they are not going to ask anything related. So unless otherwise I categorically specify that some particular link is a flexible, always you assume that the link is a reasonable rigid, okay, or resistant body. So here this is the robot, okay, and in the robot we are going to see in this robotics subject, we are going to see the direct kinematics, inverse kinematics, and dynamics. So in the direct kinematics, what is going to happen? We will find the position P on the end effector for the given link length and the link joint variables. For example, joint variable in this case is the rotational angle, okay, and here also rotational angle. For example, in case of a slider joint, how much amount it is sliding, okay. That means for a given different values of link length and link joint parameter, I would like to find out the position of the point P at the end, okay. So position of the point P means I want to find out its coordinate axis in the Cartesian coordinate system, that means x, y, z, and also its orientation about the x axis, z axis, and y axis. Okay, so here how to find out this point P? For example, if the entire body, if the entire link and entire robo is a constitute of only one body, then I can easily find out the position of the P. But here what is happening? This is a fixed one, this is the fixed one, and this is the moving one. This is moving with respect to the fixed one, and again the link 2 is moving with respect to the link 1. Generally this is always represented as a link 0. Fixed one is link 0, and this is the link 1, and this is the link 2. That representation we will see in a while. Okay, so this is link 1 and link 2, and link 2 also rotating with respect to the link 1 here. So in that case, how to represent the point P with respect to the the coordinate system, fixed coordinate system that is attached to the fixed link. Why? Because these are having again different types of linear and as well as a rotational movement. So for that, what we need to do is every time we need to shift the coordinate axis from here to here and here to here and then here to here. Otherwise I will fix one coordinate axis for each link, and I will try to represent that coordinate axis in terms of the fixed coordinate axis. Okay, here what I am trying to say is, first of all we need to find out how to transfer this particular coordinate axis that I am fixing to this moving link. Okay, this coordinate axis is moving with respect to the original coordinate axis that is fixed here. Okay, let's say it is x0, y0 and then z0. Okay, always it should follow the right hand thumb rule. So if it is the right hand thumb rule, then it will become x0 here. See, you remember this, always whichever rotation we consider here in this chapter, always it should follow the right hand thumb rule. I will quickly explain, you might be knowing, again I will explain so that you will get a clear picture. So for example, this is the x and this is the y, it will follow the order x comma y comma z. So if I rotate a plane from x to y, okay, if from x to y, I am rotating from x and to y like this, I am rotating like this. So the thumb indicates its resultant direction. So when I am rotating from x to y, it is a z direction. Okay, when you rotate from x to y. Otherwise, if I rotate from y to z, then it should get the y direction. So y to z. Okay, where is y? Y and here z. So y to z, then it is representing the x direction, and x is away from the board here in this case. The yz is on the plane, that means on the board, and x is away from the board. Okay, in the same way, when I am coming from z to x, then it should represent the y here. So I am coming from z to x like this, so that it is representing y. Okay, but what happens if I don't follow this particular order? So instead of coming from z to x, I will go x to z. I will go from x to z. Then the thumb represents the y direction, but I have written the y direction in the opposite direction. So in that case, what happens? You will get the negative sign. Okay, this is all about the vector cross product. Okay, that we have already seen in the introductory chapter. So like that we need to follow the circle. Okay, so x, y and then z. Always it should be like this. Always it should be like this. And if you are coming in the reverse direction, then you will get the negative sign. You remember this because this is very much important, and this concept will come again and again, especially when you are dealing the DH parameters. Okay. So what is happening here? I have considered a fixed coordinate system here. I have considered a fixed coordinate system, and individually I have considered a fixed coordinate system on the moving link. Fixed coordinate system on the moving link. What is the meaning of that? If I stand on this moving link, then this coordinate system is fixed to me, it is not moving. But if instead of I am standing on this link, I will stand on the fixed link, then when I am rotating this particular link, this fixed coordinate system on that particular link is no longer fixed to me. Why? Because I am standing here at the fixed link, so that with respect to me, this this coordinate system is changing, okay, or it is moving with respect to this. That means I need to find out the transformation of this coordinate system to the fixed coordinate system, and in the same way I want to find out the coordinate system that I am going to consider on the link to with respect to the fixed coordinate system. Okay, we need to consider those points, you know, in the starting, and after that we need to consider some other parameters. Then after that we can find out the position of the P. So first we will start with the how to represent a point in the space first of all, and how to represent the orientation of a point, and how to transfer the representation, translation, rotation, and translation movement, and as well as the rotational movement of one coordinate system, moving coordinate system with respect to the fixed coordinate system. That is what we will see here now. Okay, so first thing is the position of a point. Position of a point. So for example, see, there are so many different ways to consider the representation of the point, but most of the cases here we will use only the Cartesian coordinate system. There are different coordinate system, but we will use the only Cartesian coordinate system. That is very much easier. What is the meaning of the Cartesian coordinate system? In the Cartesian coordinate system, we will take the three mutually perpendicular axes. Okay, for example, if I take this as the y and this is the z, y to z will give the x. X is in the perpendicular direction of the y and z, and it is away from the board here in this case. Okay, this x, y, z here, and these three axes are mutually perpendicular to one another. And here, if I consider any point P in the space, then this point can have 6 degrees of freedom. 6 degrees of freedom. Whenever I write DOF in this chapter, that means it is a degree of freedom. Okay, so what are these 6 degrees of freedom? 3 are translation, and remaining 3 are rotation. What is the meaning of that? What is the translation? That means the point without any restriction can go along the x-axis, and also can go or move along the y-axis, and also along the z-axis. And what are the 3 rotations? The point can rotate about x-axis. That means it can rotate like this about the x-axis, and also it can rotate about the y-axis and about the z-axis. That is why it is having it has freedom. It has a freedom to move, you know, whichever direction it wants. So how many degrees of freedom it is having here? 6. For example, if I restrict this point, I will say that you cannot go in the x direction or rotate about the x direction. That means it's a degree being curtailed by 2. That means there are 2 constraints I employed, so that a degree of freedom will become 4. Okay, this is easy concept. So here, this is the degree of freedom, and we want to represent first of all this point with respect to this Cartesian coordinate system. This is a simple basic, but anyway I am just brushing up, so you can, you know, if you feel bored you can watch with a double speed also. So let's say this is the fixed coordinate system with the origin O. Okay, so here what is happening? If I connect these two, this is represented as a vector, something like a P with respect to the point P with respect to O. Okay, see here many of the times we will use this representation. For example, here the point P I want to represent with respect to the point O or coordinate system O, then it will come here. Okay, or if I want to represent something else like a point B with respect to point O, then the B point will come here. That means whatever comes at the top, that is a with respect to. For example, here I am moving with respect to this board, you know, like that we will we are defining whichever is at the top, that is a reference point. Okay, and this is to be compared with the reference point, whichever we are taking as a subscript here. All these notations followed as like in the Professor Ghoshal book. Okay, I am following everything from Professor Ghoshal. Okay, so because I studied this book only when I was in the I was doing masters in ESE, so he is my guide and that. So we are representing the same representation that he followed in the book. So here I want to how to represent the point P here. Point P with respect to A equal to, okay, so if I consider if I consider the unit vector along the xyz, x bar, y bar, and then it is a z bar, okay, unit vector, then how to write this? So for example, P is having the projections px, py, and pz onto xyz coordinate system. Then I can write px into x bar plus py into y bar plus pz into z bar. Okay, this is a simple concept, but here we need to remember carefully, like what is the meaning of the px? Px is nothing but a projection of p on x-axis. X-axis where the unit vector is x bar. Okay. In the same way, what is the py? Projection of p on the y-axis. Okay, where y bar is the unit vector. So here, whenever you write a projection of any arbitrary line onto particular another line, then you will get the projection in that particular line on which you are going to project. And pz is the projection of the projection of the p on z axis in the z direction. Okay, this is a simple way of representing this. For example, here instead of bow, I assume this has a coordinate A. Coordinate system A. Okay, that is what we are going to assume most of the cases. So here I want to represent the projection of point P with respect to A. So in that case, I can write a px into xa bar. Sometimes I may not write a xa bar. Don't confuse that. If I don't write a xa bar, it may not be unit vector. See, most of the time, the coordinate system or whatever I take here is in terms of the unit vectors. Okay. So here, what is the A? A is the coordinate system that is attached to these vectors. Okay, that means xa bar is the unit vector along the x-axis in the coordinate system A here. So instead of coordinate system, if I have a coordinate system B, then I will write a exab. Okay, so here again this is a ya and then this is a za. Okay, this is how we will represent any point in the space here. So here it is only translation movement. What is the meaning of this? For example, the projection. For example, if I want to reach the point P starting from the A here, origin, then what happened? So px distance I will travel along the x direction. I will travel along the x direction, and py direction I will travel along the y direction, and then after that I will travel z direction in the upward direction. Okay, so that I will reach finally this point. I will reach this point. Okay, so that is how we need to represent the point.